Continuing the random clock talk by J.M. Huckabee, let's look at this little AWI trapeze movement again and go into another facet of clock repair. This is the movement that we extensively use to show assembly, disassembly, escapement adjustment, and repivoted and arbor. Let's see what we would do about the problem of a missing tooth in a wheel. Let's, just for the sake of something that is nearby, easy to see, and not too difficult to do, let's imagine that this wheel that drives our hand has a broken tooth, a missing tooth, or whatnot in that wheel. Let's pull that off and deal with that particular clock problem. All right, we'll slip this clip back on here and set that aside so we won't lose the clip or the other wheel. This is the one that we will work with, and let's imagine that we have a single bad tooth in here at some place at random. Now, initially, let's discuss the philosophy of what we will do. This wheel is in a low-stress position in the train, and it is feasible to install a single tooth in this wheel and work it out with just hand tools being a saw, file, etc., and get an acceptable repair that is not very visible under casual inspection. It's highly improbable that we could replace a tooth that the most critical eye couldn't detect that has been done. Even if we place an insert in the wheel and come back with a wheel cutting engine and recut the tooth, it's highly improbable that it would be undetectable. But let's do a job that is considered in among the craft as being an excellent job of replacing a tooth. Now the question is, how is the tooth placed in there? How is it held in place? How is the profile finished out? Well, in this discussion, it's possible to silver solder in a tooth. It's possible to rivet in the tooth, lock it in with a dovetail, possibly soft solder, many other things. But in replacing a tooth, and in the trade over the years, I've seen many methods. One is just to saw a deep slot and place that tooth in there as a wedge, and that wedge is soft soldered in place and dressed up with a file. That's probably the quickest, the easiest thing that can be done, and in a low stress position of the train, such as this wheel is in, a good job could be done that way, and it would be completely satisfactory for the remainder of the life of the clock. On the other hand, if this were in the train somewhere where the stress is high, let's say the great wheel or down near the great wheel, that probably would not be satisfactory. A little sliver-like wedge, soft soldered in place, probably does not have enough strength to remain in there over a long period of time. If we should elect to use that method, we probably should dovetail back in this region, lock in the piece that we're replacing, have a very tightly fitted sweat soldered joint, and then work out at least 2 teeth or possibly 3 to do that. If we silver solder it in, the pros and cons of silver soldering: the silver solder will hold that in essentially with the same strength as the parent brass does. However, the silver solder, the heat that's required, will anneal the brass, and the brass will become softer. That is of no consequence in the low-stress area of a train. That would work quite well in this particular instance here. considering all of the circumstances, I think that probably the thing that is the best compromise, and I don't mean a compromise in workmanship, but the best all-round consideration is to cut the tooth space out rather deep, insert a piece of material, and make the joint line very close fitting, sweat it in place, machine it down, and finish it, and it should be only detectable by the tiniest white line in the sweat joint region. I think I would use that as an example or a demonstration in this particular wheel. We'll take a saw, we'll just saw out one of these teeth, we'll just arbitrarily pick one and saw it out, and we'll slip a piece in there and do that. Now, let's go to the philosophy of how that we handle this. If we attempt to make that tooth and soft soldered in place, or silver soldered in place, or riveted in place, or whatever it might be, if we make that tooth and place it in the wheel under that circumstance, we'll make a mess out of it almost certainly. Because to hold the piece while it is placed in there and get the good solder job and make an undetectable or essentially undetectable repair is just about beyond the ability of any craftsman. The thing that I ascribe to is that and this is what I'll use, we'll cut a section down into the wheel here. We'll take out a tooth, and I like to take the tooth out beginning at the root between two teeth, right in the root of the teeth. Now, if it is not feasible to do that, I just simply span an additional tooth in the wheel, make an extra tooth in the wheel. It's not all that big a deal to do that, and it improves the job, the ease in getting it in place. I like to use a piece of material that is thicker than the parent material of the wheel. Now, what that permits us to do is to let the piece that's placed in overhang on both sides. I like to let the end of it hang out maybe an inch or more beyond the wheel. That gives us the handle. We hold the wheel, we hold the piece that we're placing in it, hold the piece that's being placed in it. We make up our joint, we secure the joint, and we cut off the handle, and then we trim on both sides of the wheel to reduce that to the thickness of the parent wheel. Now, in doing that, we can have a nice finish on the back side, a nice finish on the front side, a nice finish on the radius. And we can do this trimming, if the wheel runs good and flat, we can catch this in a collet in the lathe, and we can machine the excess off of the two sides right in the lathe. So that becomes relatively easy to do, and we'll make a nice looking job. Let's approach our job on that basis. I'll pick up a saw here, and we'll just prepare a broken tooth. We'll call someplace here a broken tooth, and we'll saw that piece out and go right back in with another. This is caught up a little bit high to saw here. Let's see how sturdy it is. I think we'll be all right there. And we'll take this down to almost we'll carry this down to almost the underside of the wheel. We don't want to cut the wheel in two, but we'll go down into that region. Go into the second tooth over here, second space. Do the same thing again, and a little more to get these equal. Isn't it a shame when we just take a nice, perfectly good movement and just pick the saw up and saw a tooth out of the wheel? I don't suppose it is. After all, if this teaches a craftsman to be a better craftsman, the loss of the clock movement, even if we lost the entire movement, is well spent. This is sawed out pretty crooked. As a matter of fact, it's pretty much deplorable. Now we start working on it with a file. We'll pick up the files and continue. Back on the camera, we have a block of assorted files here, and let's work out these sides approximately straight, the bottom square, so that we can fit a piece of brass right down in there and hook up nicely. Get the eye loop and see what we have here. Let's look in that. I think I'll trim this side a little more like that, bottom a little deeper in this region, and look again. I think we'll just take that right there. Now, let's see if we can see that. Well, we may or may not be able to see it. Look in the camera right here. Let's see if we can find that. Let's turn it over. Maybe we can pick up a reflection that would be more visible in. Right here is the area that we removed. Now, if we intend to sweat in a joint there, we need to polish, not polish, but we need to cleanse the area adjacent to this. I'm cleansing the area adjacent here with a file. This particular wheel looks like that it might have a little bit of lacquer on it. I'm not sure whether it does or not. Looks like it's a little bit of very thin lacquer, and I'll rub that off so that we can get on to that area there. This wheel apparently was cut from this side, cut from the side we're looking at. Has a little bit of burring on this side. I want to remove that burring in this area, and of course we'll polish this when we get the new tooth in place. See how we look there now. All right, we've pretty much got the burrs from the wheel in that area, and no, a little more yet, just a little bit more. Let's work on that. There we go. We shouldn't have any problem in getting a very small quantity of solder to take to that, because all of these surfaces have been cleansed. Let me go off the camera. I'll go search for a piece of suitable material to insert in there. Back on the camera, we picked up a little scrap of raw material here. That's a piece of brass that we look at as 50 thousandths of an inch thick. This particular piece we're looking at is 40 thousandths. That's the type of thing we need, a little thicker than the parent stock. And let's look at a little trick here in cutting that section off. Suppose that I measure right in here. I find this is about 1 inch 20 thousandths. It's about 3 millimeters in round number. I'm going to lengthen this out to about 1 inch 30, not 1 inch, I'm sorry, 120 thousandths of an inch, which is about 3 millimeters. I'm going to lengthen it to about 130 thousandths. Let's look at the piece of stock we have. From time to time, I stone my caliper right around this corner here with a stone. This is a hardened jaw caliper. And consequently, I use that as a scriber. I can do this. I can scribe a line to the dimension that I'm looking for there. That wears out the end of the caliper. In some schools, that's considered to be bad workmanship. But in my school, I purchased the caliper with the intent of doing that. And as this becomes dull on the corner here, I close it up, stone it back, and use it again. Do that for years and years. So I do use that unhesitatingly, because that's one of the purposes that I have in the caliper. I'm going to cut this piece out along that line. I'll saw along that line. I'll take a little piece about this long, in case you can't see that very well, about 3/4 of an inch long, and we'll use that for the handle as we work that piece into the wheel. I'll need to get the bench pin, that's the sawing aid. I need a finer saw blade than this. I started off with a larger blade so that you might see it better on the camera, but I'm going to use a considerably smaller blade than that, and I'll turn off and gather the tools. We'll be back here in a few minutes and we'll saw this piece out and begin to fit it into the wheel. We turn the camera on again, and we have the piece. Let's start sawing. This is the bench pin, which we demonstrated on some earlier tapes. And saw. I have a little problem seeing here. I have a little problem seeing here, because I usually sit on a low stool with my eye at about the level of where I'm sawing. That gives me the ability to look into the cut with an eye loupe. I'm sitting on a taller stool, more at the camera level right now, and you probably noticed that I use a little watercolor brush here, and I touch that blade. I need a little lubricant on it. Ordinarily, the best lubricant that you can use for a saw blade is strap a piece of beeswax over it. In the absence of a piece of beeswax, a little piece of candle wax, a small candle works well. I have a piece of beeswax somewhere here on the bench. I misplaced it, but I should be ashamed of that situation, because right out the window that's to the right of me here, about 30 paces away, here on the ranch we have about 15 to 20 beehives. Those beehives provide us with several hundred pounds of honey every year. And in addition to that, we have the beeswax. As a matter of fact, I saved the beeswax and melt it up into pots, rolled it, and sent it away to have it milled into foundation. Been a beekeeper all my life. My earliest memories in southeastern Mississippi was the beehives on the farm there. We call farms ranches here in Texas. All right. We'll pick the end of this that looks the most suitable to file up to fit in this hole. Let me get back on the camera here. No camera operator here. I'm the whole hog in the JB shop, so we have to run the camera. You see me staring around here and there, looking into the monitor on it, hunting up the tools, sweeping the floor, and everything. I think I'll just get me a file and work that piece right in place there. Looks like that's a good starting piece. We start off here with about a 6-inch mill file, and we'll sit this piece in the vise. I want to file lengthwise on it, like this. And the question is, how do I know when I get there? Well, I really don't. Let's take a look from time to time, see what we're doing. And more to go yet. I placed this in the vise, I believe, in the opposite direction from the first time. Continuing to file on it. What if I overdo the situation? Suppose I cut it too small. Well, if we do, I'll show you how to cope with that also. Looks like we're coming on pretty good there. Pretty good. Got some more to go. This is a thing that the more you do, the easier it is to do, because rather than working to an absolute measurable dimension, you're comparing an eye view to an eye view and then working on that basis. All right? I'm getting closer. Now I need to work on the tip. Let's go across the tip, about this angle, and look again. A little bit tight, a little bit tight. I get back on the clock, on the camera. A little bit tight there. Need to work over here a little. I work all up and down the bench here. I believe this bench is, oh, it's 8 or 10 feet long, and I usually do my sawing and my filing and whatnot on the other end of the bench, but I've been working today in making the gears that we find earlier on the tape, so I was just landed on this end. Now, I've reached the point that, so what do we do if we overdo it? And that's the point that I'm in. Let's correct that. Excuse me for reaching across the camera there. Just happened to be, that's where the other end of the toolbox is. We take this, tap it just slightly with a hammer, and let's see if we can tighten this thing up to, we want this piece to go in there skin tight. Skin tight. We want that solder to do nothing more than a binder of a line contact piece. You need to turn that camera differently. What do we have here? Look at this situation very closely. Be sure that I can recognize top side from bottom side. Okay. Slight touch there. I'm going to call in my mind the pipe facing me. I'm going to call that the top side, and I'm going to strike a little bright spot right here back on the handle that recognizes top side. So when I get into a press and what I'm doing, when I'm soldering, I can find my way out there. Okay, we're going to soft solder this thing in place. Another reason that I wanted to soft solder this in place today, it's a cold day outside here on the JB Ranch. Out behind the house we have a large workshop out there that has a pretty nice machine shop in it. It's got woodworking tools, it's got metalworking tools, large metal working engine lathe, large milling machine, 3 drill presses, power saws, hand tools, just about anything that your heart could desire in the way of ranch maintenance equipment. And among that is my silver soldering equipment, my acetylene brazing and welding equipment, and electric welding equipment. And today I just simply want to go out in the cold, and we'll do this here and show what kind of job that can be done right here on the spot. Okay, I fit pretty good there. Matter of fact, I'm pleased with that fit. I need to gather up my soldering tools and be right back, and we'll put that in place. Returning to the camera, the first thing that we want to do is to tin the two pieces quite well. And as we look for the methods to do that, soldering instrument I'm going to use is a Weller soldering gun. No, I'm sorry, this one says Archer on the back side. That would be a Radio Shack gun. I have a Weller gun out in the shop. This is a little suede shoe brush. We pull the heat on it and get all the dross off of the tip. And we're going to use some solder here. This particular solder, this is soft solder, it's radio solder. This is called eutectic solder. It's about 60% tin, and the remainder, about 40% lead. This is an expensive type of solder, but it is very fine when we begin to use it and see how well it performs. What the term eutectic means, this is the type of solder, eutectic solder, that we used in IBM. Eutectic means that the melting point and the freezing point of the solder is one and the same. It's a little under 400 degrees that this solder melts, and it melts at the eutectic temperature. I believe it's 376 or 378 degrees Fahrenheit. It melts at 378. It also freezes at 378. Now, most other mixes, if we have more or less proportions of tin or lead, we find that we have a melting point at one temperature, and then we pass through a plastic region as it begins to cool. It turns from liquid to a plastic region, and then to the freezing region where that it sets. There is no plastic region in a eutectic mix, and the mix that is attributed to have that characteristic is 63% tin and 37% lead. Now, that means that it is much easier to handle without getting a bum joint. If we shake the joint while we're in the plastic region, we lose the strength of the joint. Now, I'll set this here. I only want to touch in that section of the wheel, only in the section of the wheel that is important to us. And I kind of whipped this off here behind me, and I don't believe I got all the solder off, but let's try it and see. We'll do this again and see what we have. We want to remove all of the solder except just the tinned film. All right. Now let's see what we can find here. Find a pointer, and we have a line around this notch that we've cut out. That line that's around the notch. See if I can find a place in the here that we can see that. There's a line around that notch that is white that is about in the order of about 50 thousandths of an inch wide. Now I want to look down in here and be sure that all the surface is picked up my glasses that didn't have the eye loop in. Changed to another pair of glasses here. Okay. I want to see that the entire surface inside there is tin coated and that there is no buildup of the solder. The purpose of that is I don't want to build up. I want to be able to insert this piece in there just as I had cut it. Snug, snug, tight. Now, let's tin the piece. We'll take this out of the hand vise. It's not a pin vise, it's a hand vise. And let's tin this piece. Okay, fire the iron up again. We'll brush the tip as it heats up, get all the dross off of it. Come up here and we'll give it just a moment to get blazing hot and do this again. And at that point, I shake off all the excess solder. Let me look. I get my cap out of the picture again. Let me look to be sure that it's perfectly tinned, and it is. Now, at this point, we have to hold this in place and touch down with heat. When we touch down with heat, we will seal those joints together perfectly. All right, let's find again our top side. We'll put top side. We'll put top side of this piece where the nut is, and we'll have to hold this in the pin vise or whatever. I mean, in the drill press vise, and we need the ability to hold this so that it will not shake, so there's no possibility of shaking that when we touch down again with the heat. All right, let's see what we can find. Here's something approximately high enough. The vise here is too low, so we need to raise that. I'm looking for something about the bench to set the vise on. How about the range pocket knife here? See if we, that's too shaky. Can't use that. Well, try this. Here's the bench pin, and we'll let this down. Lots of good tools made for holding this type of thing together. They're mostly in the electronics industry. I'm going to hold this one down with my fingers over here, but I'm a little bit squeamish about this thing rocking. Let's try again. That looks better. Have to lift a little. Right here. I'll hold the pressure on that while we bring this iron up to iron. It's a soldering gun, soldering tool. I'm going to touch a little solder on the tip, get it blazing hot, come up and land down on this. I see this flow all over. I'll stroke the soldering tip away, which will draw away the bulk of the solder from the area. Turn it over and look at the bottom side. No, we didn't have enough heat on it. The melting did not travel completely through in the joint line. Let's do it again. All right, I think the thing that was happening was getting a little warm on the fingers. Let's look on the bottom side again. We need a little more touch under that. I believe I'll turn this over and send the heat from that side also. We'll set this so that these two are same height here. And we'll clean up the tip again. And there we go. Okay, touch down here. All right, we look good. Now, I wish that it were possible on the camera that you could see the flow of this solder right here where this piece is. You still have the handle on it. The thing that we see, it is perfectly smooth. It is just glass smooth on there. There's a little bit of rosin flux. The flux that's on this is nothing more than pine rosin. We'll scrape a little bit of that off, and we'll look at the joint a little more careful then. Continue to scrape off and to scrape off. So let's look at that with the eye loupe. And that looks completely satisfactory for the insert. All right, let's cut the handle off. Remember the ground rule: make a part, make it with a handle on it. Let the last operation be cut the handle away. We'll dispatch the soldering gun, and we'll look for the handsaw. We'll saw this off a little bit longer than the tip of the teeth. We'll leave the standing proud beyond the periphery of the wheel circle ever so slightly. This morning when I was sawing on that piece of plastic, I like to cut the end of my finger off here. I had boasted a few tapes back, am I going to cut my finger? No, no problem, no problem, no way. If I start cutting, I'll quit pushing. Well, I ate those words this morning. Cut the end of that finger there. It was just a tiny little cut, but it bled profusely. Put a Band-Aid on it, and it stopped immediately. Now, let's take a coarse file and pick up some of the excess of the solder and the excess of the thickness of this piece. Recall that we said that the piece that we were adding in is thicker than the parent material, so that we can dress down flush on both sides to have a nicer finish. Let's get a coarser file. Why do we want a coarser file? Well, the main reason we want a coarser file, if you get one of your fine files loaded with soft solder, you're in a problem. It's easier to unload the solder from the coarse file. We'll take this down till it appears that I'm about to touch the teeth. I want to be able to see the added piece of metal that is in there. Okay, we'll turn over and do likewise over here. I think I'll drop this pipe in the vise. Save myself some holding problem. There's a little V-notch there. That will help this. You have to be careful here. If we overdo this situation, we'll put some scuffs in the sides of the wheel that will be difficult to polish out. We're getting close. We're getting to slightly touch the wheel here and there, and we're just about there. The solder has all but disappeared from the surface of the parts, and the two parts are flush, the added piece to the apparent wheel. Just a little mite more here. You hear the bell ding then? That's a warning to me. I have to run an errand. Here on the JB Ranch, we have wells. We pump our own water. We've got a 1,200-gallon ground level mounted storage tank just outside the window here, about 50 paces. And we have the pump that's pumping into that tank. That's the estimated amount of time that it would take to fill the tank. Also up in the pasture area, about a couple of 100 yards away, we have another deep well that has a very fine submersible pump that's about 300 feet deep in the earth, and that well is capable of producing about 40,000 gallons of water a day. You're on the ranch, you have no fire protection and fire department and whatnot. We keep about 3 acres of land right around the house proper, sprinkled enough that it's green, not golf green type or not city lawn type of green, but green enough that it is a fire break around the house. In summertime, we've estimated that we use about 10,000 gallons of water a day during the months of about late June through the about the end of October. But the bell that we heard there just a moment ago is the bell that says that I expect that 1,200-gallon tank that supplies our house here to be filled right now. As soon as I follow this a little further, I'll cut the camera and go out and cut that pump off. We're certainly blessed in having an abundant supply of very, very good, sparkling, clear water here in this area, and it comes from the two wells. The well that's running right at the moment for the house has a windmill on it. As a matter of fact, I can just tip my head over here about 6 inches from where I am, and I can see that windmill running. It also pumps. It's running slowly now. It's pointing to the southwest. Looks like the wind might be about 5 or 10 miles an hour. It's just turning gently. We're just about to the end of the filing operation. And there we are. Now, if we look at this, let me inspect this before I buzz off here. There is a very, very fine, just an extremely fine line that we can see the sweat joint of the solder and the piece that's inserted in the wheel. Now, let me run this error and we'll be back and work on this gear some more. Back on the camera, we've had a lapse of about 5 minutes, and indeed the water tank was full, and 1,200 gallons will run us about 2 days. We fill the tank every day, and that particular tank just supplies the water for the household here. Everything that's in the yard, in the pasture for animals or whatnot comes from the other well, and so we have our water supply, which would carry us through probably through the day Monday. Today is Saturday. This is Saturday afternoon. It's about 2:30, and it is the 28th day of November, 1987. I'm J.M. Huckabee. I'm knocking on the door of 66 years old. Retired, doing this for pleasure. All right, let's look at the, I got carried away and got out of the camera. We look at this pipe on this wheel. I'm sitting on about 199 thousandths. If you can convert metric system in your head right quick, you would know that that's 5 millimeters. So we look in the chuck block, we're looking for a number 50 collet to number 50 being 5.0 millimeters. We'll put that in there to hold the wheel. Do a little machine work on it now. All right, let's set this in here. Snug it up a little bit. We'd like for this to run very true. And tighten it up, and let's see how it looks. And I tell you, that's about as true as, when you look on that with the eye of it, that's remarkable. must not be perfect, but it sure is close. All right, I'm going to take a machine cut on the periphery of this wheel. The reason on the periphery, I want to trim down the height of the insert so that it's equal to the height of the teeth. Now I'll go on to that with a tool bit, and with that tool bit I will trim until I can hear the tool bit touching the tips of the teeth, and then I'll stop. I'm going to use and that bit is not suitable. That's a dull one. You pick up another one. I have to crawl under the camera there. Let's find a bit that has, that one is suitable. That's slightly, that one is slightly round nose bit. Let's look a little further. Here's one that's just right. All right. We're going to set this in the tool compound. Why don't I do this with a handheld bit? Well, I don't want to knock that piece out. I can pull that tooth out if I get a hang up in the lathe here, and I don't want to take the chance of pulling that out. Consequently, I'm going to use a pointed tool bit. I'm going to run it slightly below center. It has adequate rate, and I want to very slowly, very gently take off the excess. Remember, that's an interrupted cut. That's the type of thing that is prone to hang up and problems when you're machining. I'm going to run pretty fast here. I'm going to move up the speed on the lathe, and let's see what we can do. Down here in eyeball range. I touched that up a little bit with a file while I had the camera off. I can hear the bit touching. Let's stop and see what we're doing. We are touching the, I thought at first that I might not be touching the insert piece, and I might be touching a tooth, but not so. I'm touching the insert. I can hear it, I can hear the cutting noise at the rotational rate. I haven't come down to where I can hear a tooth yet. And we continue. And continue. I had expected to begin to hear the teeth by now. Let's take another look. I'm covering the full breadth of the piece, and I can see the adjacent tooth is just a little bit low. Let's go a little further yet. I can just hear a little sing. I'll pull up about 1/1000th of an inch. Listen carefully on the camera. You can probably hear the saying of the teeth. You hear the saying of the teeth right there. You hear the saying of the teeth and the piece that I have. I'm touching down. Let me see. Matter of fact, it's difficult to see where it has touched the teeth. Now I have this height. Have the height of my insert exactly right. Now I want to go on to the side of this and face that ever so slightly. Matter of fact, I've already filed that down. I believe I will not go on the side of it and face it. I believe I'll go on the side of that with a piece of abrasive paper and I'll polish that up. Let's find a suitable buff stick here. There may not be one in the house that's exactly suitable. Everything that I keep over here is very fine. It's a leather buff and a flannel and another felt, and this is a fine one. I didn't prepare in advance for this show. Here's one that will do that. Let's see what kind of success we're having. And it's looking good. We've got some distance to go. We're doing all right. This wheel is not running quite as true and flat as I thought it was. I can feel ever so slight tremor in it. Again, it's a pretty fine buff. I believe the abrasive on this particular buff is 380 grit. Every scratch is gone from that. Let me pull out and look there. There is not a scratch to be detected anywhere on the side of that wheel, and where the insert is in it, there is a white line. That line is probably ranges from maybe 5 to 7 or 8 thousandths of an inch in diameter. Is all that can be seen. You would have to look very carefully. You would have to be an astute observer to find that joint line. Now, let's see if we can do the same thing on the other side of it. I'll go on the underside here, get in that, and polish off from that side. Remember the criteria that we're working to now is that this job is not to be readily detectable. We want this job so it's essentially undetectable to the skilled eye. That's a pretty big order. Pretty big order. Let's look again. And I'm okay on this side too. All right, on this side. Now comes the critical situation. See, we're perfectly flush. I can't feel that right here. We're perfectly flush. I cannot feel that joint line there. I cannot feel the joint line on this side. The periphery of this. When I run my finger around it, I find a smooth spot, not a high spot. Now, we have to mark out our teeth that we're going to cut. Now, that's not easy to do. That's just plain not easy to do at all. But if we hook this, let me get the camera a little lower. Using this caliper as the scriber, if we set this up so that we can hook onto the edge of one tooth and span to the edge of the second tooth. We're hooking on one tooth and span exactly to the edge of the second tooth. Now, if I do this carefully, I'll go in here and I'll ride the edge of an adjacent tooth, use this as a scriber. I'll draw the image of a tooth on the part that I want to trim out, or the place that I want to do the trim. Go over to the other side, do the same thing. I wish that you could see what I've done here, if you could see what I've done, I ride the edge of one tooth, come over here, and scribe the adjacent one. And then do this again, get back over here. With that scriber, I'm riding the edge of one tooth, going over here and scribing the shape of the one that I want to cut. Doing the same thing over here. Now, in doing that, I have a line that I can saw to and that I can file to that carries me the same profile of the tooth that was originally there. That's a trick in trying to find your way and your shape. Now, to me, the easiest way to approach this is to saw this out. Now, sawing it out, if you're not adept to sawing to a line, you're in a heap of trouble there. What I will do, I will put in one of the smallest of saw blades. I'll get this where I can look at it with a good strong eye loop, and I'll saw that profile out. We're back on the camera now, and while you were away, I was busy doing something else here. I'm sitting on a low stool. My bench pen, I have several of these bench pens. This is one I use in the drill press for drill stop. I drilled a hole there that can accommodate the hub of this wheel, so I can make it lie flat while I'm sawing, or essentially flat. This wheel has a little bit of cut to it, and so I can hold this to saw there. I picked up a saw blade, the tiniest saw blade that I have. You probably won't even be able to see it, and I'm going to have to get my head with a strong eye loop right down over this to do this work. And I think what I'll do is turn the camera off, and we'll see about how long it takes to saw this out. It is 8 minutes till 3 o'clock on Saturday afternoon here at the moment. I'll cut the camera and we'll cut this out in the rough and see how long it takes. We were making an inserted tooth for this particular wheel of this little trapeze movement. And we were timing the period of time that was required to saw the replaced tooth. See if we can find the tooth. Find the tooth here. We were sawing the profile of that tooth at that particular time. What I didn't realize that was happening was that the tape expired while I was getting the saw together and sawing that out. The time that was required to saw that was something like 3.5 minutes, and began to file the profile, and not realizing the tape had expired, I finished the job of filing up the profile on the tooth, and I can't retrieve that without sawing out another tooth. So let me tell you how the situation wound up. We sawed the tooth to the scribed line, around it with a very fine saw. Then following that, I went in to the tooth and dressed it out by eye with some very, very small needle files. The files that I originally chose were a bit too large. I used these very small needle files. This is about 4.5 inches long, including the handle. So we filed out and finished out the tooth, and as this is finished out, I caught this in the chuck of the lathe and polished this side of the wheel, caught here in the lathe, polished this side of the wheel, polished this side, and looked at the tooth edges for possible burrs. Then I brushed that, brushed it vigorously on each side, with a little suede shoe brush, a little brass bristle, soft brass bristle shoe brush to deburr any possibility of a sharp edge that might be on the work. And we went back into the lathe and polished it again. If we take a look here, we see that the wheel is very bright from the light reflections. Likewise on this side, and it would require a very, very careful inspection to find the insert. I can look around this insert. I know what to look for so that I can locate it. It is right here, right in that area. The thing that I detect it by is not by the color of the brass or the insert or whatnot, but that sweat joint is no more than 2 to 5 thousandths of an inch wide. A tiny, tiny white line can be detected there in that joint. And unless you knew to look for it and was searching for it, it would not be recognizable. Now that's the type of workmanship that we look for in inserting a tooth. Now let's talk about how good is the job? Does it work? Let's do this. Let's go back to the depthing tool. We used a depthing tool on some previous tapes. And let's take the distance. Let's look at the center distance. Let me get an eye loop to do this better. Eye loop built into the glasses here. Let me look into this and get the spacing of this depthing tool equal to the spacing between these two wheels here. Okay? We have the spacing on the depthing tool runners now equal to the distance between the center shaft and the stud. Get back in the camera, between the center shaft and the stud that these wheels are operating on, their center distances. All right, let's drop these in the tool. We'll set this one right here. I believe I'll use the point center on both ends of this one. We have the point on the end of that. We want this to be perfectly free, but with no slack. No slack, yet perfectly free. Essentially zero clearance. This one must go in with the pinion here, this pinion, meshing with this gear back this way. This is top side. This is the toward the hands, toward the face on the clock. This is top side. I call this movement top side. All right, we'll sit this down in here. I think I'll send this, well, I don't really know. Let's send this center in to about this runner to there. Now I have to turn this one in the opposite direction. The 2 points will meet each other in this particular situation, and have to be very careful that there's no bind and no slack. That's the condition that I'm looking for. I don't know if I'm going to be able to get that condition because one end of my runner is not a good fit to the gear. Put this one over a bit. See what we have now. Let me turn this around the other way and see if I can do better. I wanted to demonstrate this in the on the spacing and the depthing tool. Here we are. Let's try this. Can we see the wheel spin? And there's no indication. And let's take this past the insert. I'll have to locate the insert now. Okay, it's about, no. Having trouble finding it. There it is. The insert is right here. So we turn down here, and I'm going to look for backlash as we go around. As I progress around, there is a small degree of backlash as we pass over those teeth, and absolutely no binding. See this band here. So now let's examine the criteria that we were working to. First, we said that it had to be totally and completely functional. No compromise in the functionality of the piece. The second situation, it had to have a life expectancy comparable to the remainder of the wheel. That is, that it has to be of similar material, it must be very secure in place, and its appearance and finish should be like the remainder of the wheel. And thirdly, that it would require a highly skilled eye to detect that it's there. We can answer yes to every one of these things. I believe that in the assessment of a skilled craftsman, that as he would look at this, that he would undoubtedly say that this is an excellent job of replacing a tooth in a wheel. Now that's the type of, or the class of workmanship that we would like to aspire to. Now, this movement has been used for several demonstrations here, just recently in these random clock talks. If we examine it, we would, I'm looking for a little clip that goes with it, right here, that holds this in place. We have repivoted a wheel in it, and the repivoting job, if we look at that, and I'll have to find the, this is the pivot that we placed in it. I would just about defy a craftsman in finding that that is a repivot job in the movement. If you pull the arbor from the movement and look into the end with a strong glass, possibly some detection of the joint line may be found in there. But we've repivoted a wheel. We have put teeth in a wheel. We've had this up and down a number of times. We've discussed the pendulum, the aspects of that, the assembly, the disassembly, the escapement adjustments, and whatnot. So we would say that this little trapeze movement has served us well in a considerable amount of instruction on these random clock talks. We'll bring this random clock talk, this particular one, to the end. I'm sorry that I ran over the end of the tape unknowingly, and you did not get to view the actual sawing and filing of that tooth. When I realized the tape had expired in the camera, it was too late.